degree of the map. The degree of the map is D if not both. Both of BD and zero. So at least one of them is 0, and you can view these two cases as two charts on this space, if you like. And they should have no common zeros in the denominator and numerator also. So of denominator. So yeah, so this is a space of this is a space of rational maps of degree D, and I denote it by RD, the 2D plus 1 complex dimensional manifold. Okay, so this is the space, and yeah, then you have critical points, which I denote by crit. So critical points of F is a set of points that where the derivative is 0, using spherical metric, spherical derivative here, and then you have the post-critical set. Which is denoted by PF. Yeah, this is the forward union of the critical points. And then you take the closure of this thing. And this is the post-critical set. And then if the definition F is hyperbolic, if this set does not intersect the Julia set. This, I guess, quite well known for the audience now, but this gives a uniform expansion of the Julia set. On this Julia set, JOF, this is the Julia set. Of F, and so these maps, again, they've been talked about. This conjecture that they should be open dense. We're going to talk about these Collet-Eckmann maps. Allows this is a kind of class of non-uniformly expanding maps. And there are, well, many classes of this, but I'm going to focus on this Collet-Eckmann class. Let me define Collet-Eckmann maps. Not all of you have seen this. So I usually include non-hyperbolic definition. Non-hyperbolic map, rational map, if it satisfies the Collet-Eckmann condition. It says, yeah. CE map, Collet-Eckmann CE map, if for each critical point in the Julia set, we have the following. The derivative is of Fn of f of c. This grows exponentially for some constant c. Well, there is some constant c. I should have that before. Which that. Okay, c times e to the gamma n. And of course, this is if there is no other critical points in the forward orbit of c and so on. I don't write it on the board. I just say, okay, so you have the critical points on the Julia set, iterate them forward, and then as long as you don't hit any other critical point in the forward orbit, then this is 0, of course. So doesn't make sense. Then you have this kind of growth for some uniform, where C here. These are constants, which yeah. positive constant C and gamma. And then there is this old theorems about absolutely about existence of invariant mesh and so on, and well, conjecturally these maps, well, as in the quadratic family, real quadratic family, is almost every map is like this, or is hyperbolic actually. So it's another version or stronger version of the conjecture. But anyway, so there is some old theorems by Rees, why there exists a set C in this space of rational functions. If is 2 at least, and of positive Lebesgue measure, this C is as positive Lebesgue measure. Such that any F in this set has bits absolutely continuous invariant measure, and then in my thesis I wrote another version of this theorem for Collet-Eckmann maps, and so if formulated like this, if F, if this is a rational function, is post-critically finite, we know this already, we have defined this, somebody before me. Post-critical set is finite, and the Julia set of F is the whole Riemann sphere. Then F is a big density point of these Collet-Eckmann maps. Okay, so that's old, and this gives a news by results at Przewalski and Grachik-Smirnov. For instance, this gives new proof of Rees here. Okay, so you have this measure for those Collet-Eckmann maps also. Okay, but these post-critically finite maps are of course not recurrent. There's no recurrent. They're not recurrent. Critical points do not return to the neighborhood of the critical points. So I'm going to consider perturbations of a wider class than these post-critically finite maps here. So I'm defining now what does it mean by slowly recurrent. So a map F is critically slowly recurrent. This definition I got from the paper by Levin and Shen and Francine, I think. It's in the literature already. So slowly recurrent if for every alpha greater than 0, we have that the distance of the iterates of a critical point and the critical set. This is well, it's allowed to go to 0, but only at this rate, minus alpha to the n, for sufficiently large n. And where C is in critical set, yeah, in the Julia set. Usually I denote this by the Grit, this set, critical set on the Julia set. But not that, but Grit instead. I don't know if it's a good notation or not. Doesn't matter. So that's those slowly recurrent maps, which I want to perturb instead of that. that thing. Yeah, and I'm going to use this normalization by Evin talked about just before me. And then you not the renormalization, a normalization of the parameter space. Maybe luckily I don't have to define this again, but you have these sets of lambda. I think you call them lambda d. It uses notations probably, but this is a set of you have fixed certain set of rational maps of degree d, and we have p prime number of critical points, and then you have fixed multiplicities of these critical points also. So with p prime critical points different, yeah. Critical points with fixed multiplicities. This is that's this vector p prime bars. That's this list of multiplicities m1 mp prime. So you fix that, so you don't split. There is no splitting of critical points in this space. For instance, if you start with a map where all critical points are simple, then of course this is the whole space locally. And so on. So I'm going to use that normalization when I state the results here. So there are two results which I want to state here first. Theorem 2. This is the corresponding thing to that one. But if f belongs to such as the space here D, D prime is slowly recurrent, and the Julia set is the whole sphere. Now then F is the big density point. Sorry? Yeah, sorry, yeah. Collet-Eckmann should be Collet-Eckmann. Sorry, Collet-Eckmann map. Yeah, thank you. CE map. The Julia set is a whole sphere, and then F is a Lebesgue density point of CE maps. Oh, in that space then. Okay, so that's one. Now theorem 3 or 4 or whatever. Oh. And this is together with Mats Bylund and Lebesgue. Then we just consider the case when Julia set is not the whole sphere. Again, yeah. If is a space again, P prime R is a slowly recurrent Collet-Eckmann map. Okay, SRCE map. Then and Julia set is not the whole sphere. Then it is at the Lebesgue density point. Of hyperbolic maps. these are these two theorems I want to speak about. This is one, yeah. And this last theorem overlaps a little bit with results by Grachik, Benedict, and Grachik and Swiatek. So they consider typical points with respect to the harmonic measure on the boundary of the Mandelbrot set or multiplot sets, and prove the same thing as this. Basically, there are some more geometrical things in this for those in this case. So yeah.
Just to clarify, so Lebesgue density again refers to measure on LDP, right?
Yeah.
Okay.
Well, I mean, it's just you take any family. You can take any family in this space. This is a kind of manifold locally around the function, and you will just look in the full space there, the big density in that space. But I'm going to look at small one-dimensional families, one-dimensional complex families. In this case, I will look at one-dimensional real families. So then you just to be done. Yeah. Okay, so. That's corresponding. Good parameters. So I think this is unpublished, but this is published. It's a serious paper. Okay, so I'm going to use to prove these theorems. I'm going to use Gennady Levin's heavy machinery, partially at least for that. And let's talk a little bit how to prove these two theorems. Okay, so proof. Let's look at the case. And the Julia set is equal to the Riemann sphere first, and then when it's not equal to the Riemann sphere, a little bit later. When did I start? 12. I have. Okay. The idea is to study the evolution of this, the iterates of the critical points or critical values, whatever you like, of this function. I call it psi n, comma L of A. A is a parameter, and then you have this is f a nth iterate. L stands for the index of the critical point. That stands for which critical point you're iterating. This is fn of cl of A. And here, so CL are critical points for FA. A is some parameter. You study the evolution of this. This is an analytic function for each n. This is just, and what you're going to I'm going to do is that the starting function, so f0, this is a starting map. Slowly, this is starting this slowly recurrent, call it Ekman map. That corresponds to A equals 0, and then you look around A equals 0. You're looking at the small, well, actually, you're looking at the analytic families. So actually, FA here is going to be a analytic family of maps around F0. So it's a one-dimensional. I'm going to let A be a real parameterization. So A belongs to some small interval around the starting map. And now if you use the heavy machinery of Gennady-Levin and there are some you can perturb your map in certain directions. And if you do this correctly, then you have a nice result on the comparison, the transversality result on the comparison between the space derivative of this starting map and the derivative of that map. And so what you have is that giving if this is a non-degenerate family, I'm not going to go into what that really means, but it means that you are perturbing it in a certain way. Yeah, I'll talk about the label. So FA is non-degenerate. I write in the sense of Levin. Then you have the following. This is from Levin's results directly. You have the limit as n goes to infinity of psi n comma l prime of 0 divided by df n minus 1 0 of cl of 0. So you are looking at the starting map here. No, not FL. Sorry, I want a critical value here. F0 of CL. This converges to some number L, what we call L, naturally, and this is not in 0 and not infinity for all L. You have this nice transversality idea. This means that it's a derivative here that you can sort of compare the parameter derivative and the space derivative. This is very important when you want to do this kind of you want to do this parameter exclusion techniques. So from this you can now make a small perturbation, and you can say, okay, well, as long as if you now take a perturbation of the function, you know that the starting function is a nice Collet-Eckmann map, and you make a small perturbation. It's not necessarily a Collet-Eckmann map, but as long as the derivative grows exponentially, if you can sort of verify this, then you can actually say, okay, they are still comparable. So you get a lemma out of this. So you fix some Lyapunov exponent. So you have this Lyapunov exponent, which is this exponent, but the derivative grows exponentially. This is the exponent of that growth. So for any gamma, if you choose some gamma L greater than 0, there exists, if you choose one gamma L, there exists a epsilon, so that whenever you have this derivative growth of a perturbed some parameter A, I write VL now. This is the critical value. Say that this is this grows like e to the gamma L times n. Sorry, it should be m here. So you have some growth like this up to n, and a is some parameter inside this interval which I started with. Then I have this comparison again. -1 at VL here. So this is close to 1 actually. So you can look at this. This is oh no, this is close to this LL. Sorry. the original LL, but it deviates from it very, very small, but a very small amount. Like this. So you keep, as long as you can, but you have to keep you have to sort of make some kind of induction argument to make sure that this holds. Of course, it doesn't hold always, but so now, so how do you verify that this holds for some? You fix this is some kind of lower Lyapunov exponent, which you have to choose from the beginning to be able to start the machine. The Benedict-Collet machine I'm talking about. That's an idea of how to inductively get this derivative to hold for a certain set of parameters inside here. You have to cut away parameters. I'm going to talk about that now a little bit, how to do this. So let's continue here. So what you get out of this thing is that you corollary here. What you're going to do is you are going to iterate this whole interval from the beginning. So this whole interval, you're going to study psi n comma L of this whole interval minus epsilon to epsilon from the beginning, and then this is a curve, right, in the space. Some curve. And when it comes close to the critical points, you will lose derivative. So then you have to cut away parameters.
Excuse me,
Yeah.
Magnus, I have a question.
Yeah.
So this inequality, lemma 1, it implies that it holds for a equal to 0, right?
Yeah.
Always.
Yeah.
For any n.
Yeah, for n, as long as you have this condition satisfied up to n for all m, then at this n, well, at m also, but then you have this nice comparison principle up to n. So if you can say, okay, the derivative grows nicely up to n iterates, then you can say, okay, well, then the parameter derivative and the space derivative are also comparable for up to n. But you have to choose some starting exponent from the beginning, and then if you choose this small, then you have to choose that one small also. So you have to make your perturbation small. This is like a consequence of that theorem. So this is in order to keep this. You want to transport information in the phase space to the information in the parameter space. So I will come back. This is So what's going to happen now is that there exists a curve. There exists a neighborhood u of grid f0 and some large scale s. This is some large scale s called this is of the same order as the diameter of u, same order, such that for epsilon greater than sufficiently small, there exists some number n small l such that psi n l comma l of that big interval minus epsilon epsilon grows to either, well, there are two things that can happen. Either it goes to this large scale. This is a curve which grows to some large scale. Either it goes to the large scale S outside U, or I'm going to draw a picture soon about to try to clarify this. Either it goes to some large scale, and you also have nice geometry of this curve because of the derivative from the starting map. So in the beginning, this is like in the beginning. So in the beginning, this curve grows because of this, because you know that the derivative, you're close to the starting function. You can sort of use that that information in the beginning, I think. So then afterwards, you have to do something more, but this is going to happen in the beginning. So either that or it's it goes to some dyadic or Whitney. Dyadic, nice. Well, it's both cause of nice, dyadic, nice curve inside, inside U. And what does this mean? Well, this dyadic means that there is some comparison of the diameter of this set of this curve psi n l, comma l. This set I usually call 0. So you iterate this small interval. The diameter is approximately some small kappa times the distance of this curve to the critical points of well, of those parameters. Well, so this kappa is a small number. I don't talk too much about this now. This also goes to 0, but it doesn't matter. So what the picture is the following. The picture is like this. So you have this neighborhood here. Okay, here is the critical point C, some critical point, and you also want to make this construction such that if this is U, and then when you move the parameter, the critical point will also move, right? But it moves very small amount in comparison. That should be negligible. What happens is that either you are outside and then you have a curve. I draw a straight curve here. Of course, I didn't say anything about why it's almost straight curve. And, or inside here, well, then there is some dyadic curve inside here that has to be small in comparison to the distance to the critical points. Otherwise, you create a lot of distortion. So what I mean by nice here. Nice means this, that you have a distortion control. So the NL's derivative of FA of LA. It's close to 1. It's very close to 1. 100 for all A and B in this starting interval. Omega, that's the minus epsilon epsilon. So you have this nice, very strong distortion control inside this interval. And if you look at that thing here, if you can compare these two also, you get directly that the geometry is nice. Combined with lemma 1, yeah. You get the disk psi n, comma l prime of A divided by psi n, comma l prime of B is close to 1. It's some number. I shouldn't write numbers here because then it's some epsilon, some small number, and this also holds for A and B. And so that means that it's a smaller rest, right? So these curves psi n l here, comma l, are more or less straight curves. So okay, and then what you do now in this Benedict's-Carlson construction, which is sort of this is based on, what's going to happen is that if your curve, of course, this is going to happen at some point in the beginning. When you know that your starting map is slowly recurrent, it cannot approach too fast here. But you choose an interval like this, and then you continue. And of course, this can grow more and more, and suddenly maybe it it returns like this. Now you have a problem. You have to delete parameters which are too close. Okay, so that's what you're doing, and I'm not going to do the details here. So this is this Benedict-Carlson parameter exclusion technique, which you all know. No, you don't know it, but some know. It's a complicated machine. So what you will construct is you keep these parameters corresponding to these intervals here, and you create a Cantor set of parameters which are good, which have this property. And then you can use this over and over again and construct the Cantor set of positive measure. So that's how you do it. Okay, well, let's look at the case just a few minutes when the Julia set is not the whole sphere. Okay, the case like this. Should have erased. So let me just write this like this. Okay, so have a look. This is a bit easier to see, I think. So you have the same idea, but now you start with a square. You consider parametric squares. Instead, the complex squares. So I'm going to look at Q. I call it squares Q. Q, the starting square. This is a square. This is a square, small square around the starting map. So in the middle here, you have the starting map, the parameter corresponding to 0. Small. Around 0. This is the corresponds to 0, and then you start to iterate that instead. This, you can look at this psi j comma l of q. Maybe I will just drop l and look right like this. I'll drop the index of the critical point. I'll just have it in mind. Okay, so this grows nicely again. Up to same idea as here. Large scale. I'll write it again. One large scale. And this is sort of when you're outside Q. Or up to the static nice square inside U. Of course, you can cross U, but that's a technical thing I don't want to talk about. I mean, you can this square can also cross U, but then you have a technical thing. So what's going to happen here is that this the Julia set of these maps have measure 0. Actually, so that first case here is especially good. They are called escape situations. So situations like one are good. I'm going to explain why. They're called escape situations. This is from this Benedict-Carlson terminology again. Escape. And so you start with a square, and then this is Q, and then you start iterating it. Because of the nice distortion properties, this will also more or less a fine map. So you grow with a big square like this after some time. Okay, now if case 2 occurs, then the the corresponding situation is that you have a square here instead of a line. So you have a square inside here, and or you can have a big square, whatever. So, but you have to partition this square into smaller partition elements. So you have to partition this into smaller squares. I mean, in the long run, it can happen. And then you consider each subsquare and iterate that. So no matter if you have the starting square or if you're looking at some partition element, let's call it Q and let's see what happens. So the point is that most squares are going to escape quite soon. So if you start with this situation, well, okay, you iterate again, and then you partition it, you delete parameters which are too close, you continue with the smaller squares, and so on, instead of intervals. But if they escape, reach the large scale, the size of this is S. Then you will see a copy of your Julia set inside here somewhere. And because of this strong distortion, what you're going to do is you make a small neighborhood of the Julia set. The Julia set is here somewhere, and you make not a perturbation, what am I saying? A neighborhood of the Julia set, which is much, well, this neighborhood is really close to the Julia set in comparison to the large scale. And you pull it back to the parameter square. Okay. And the interesting thing is that now if you chose now eta, yeah. Choose some neighborhood. So n, this orange thing here is some neighborhood of the neighborhood n eta of the Julia set of the starting map. And if you make that small, and then you make the perturbation also very small in comparison to this, you can say that by the green slides, by just stability out here, this is the Fatou set of the starting map. If you are to make your perturbation sufficiently small, this will still be contained in the Fatou set of the perturb map. So you fix some neighborhood, small neighborhood where n is much smaller than s. Then there exists a perturbation epsilon such that the Fatou set of perturb maps are still inside the Riemann sphere minus this neighborhood for A inside the for A inside this Q. Well, Q depends on epsilon. Q is like an epsilon square. So this you can do, and then you can put back your parameters. So if you take a parameter here, take a blue parameter which lands outside here, you know that even if it's a perturb map, it's going to land in the Fatou set. And then you can say that, okay, well, if you do this, most parameters in here are actually going to be pushed. Well, parameters, most critical points. This every parameter here corresponds to a critical point. They will be pushed out to the Fatou set. And yeah, and this is the idea. So you can sort of see that in each such square, you will have a large portion of parameters where the critical point, that specific one, is actually in the Fatou set. Okay. So yeah. So this, if I write E in the set of B in Q, such that psi n of B, yeah, I wrote it down there, belongs to the well, this belongs to the neighborhood. Should be a small set. Well, this should be a small set. So by low distortion, there exists some delta. This depends on this eta. Epsilon is a small positive number. You can say that the parameter, the measure of this is not more than delta times the measure of Q. It's small one. And of course, if you then look at HL, well, yeah, I think I will just, how many things do I have? Officially 3, okay, great. So I think I can just, yeah. So what you do now is that just say that HL is set A in the, well, let me put let Q0 be the starting square. Okay, so when I did this for any square really in the partition, but if you look back in the starting square, I mean, I said that in words, I didn't write it, but I said that most sort of partition elements will actually do this, have this escape situation. So these sets HL, those A belonging to this starting square, which have the property that the critical point will actually be in the plateau set. Well, this has a big measure because of that. But most squares escape, and the measure on each square where you have the critical point is pushed outside is big. So yeah, this is the measure of that set is quite big. So this is like some 1 minus some delta tilde times the measure of Q0. And if you are in the intersection of HL, of course, then the map is at the bottom. So this is the idea. Yeah. This delta can be made, delta tilde can be made arbitrarily small. And it depends on all these constants which I wrote at the board. So the most Q's escape, and in each Q you have this property that it's a small set that are close to the Julia set. Okay. I think I'm done.
Right, so any questions, comments? And as before, our off-site participants, feel free to unmute and just ask questions. David, run. As you can see, David is training for the race up the Eiffel Tower.
2 questions. First, do I understand correctly that you use mean porosity of Julia set for Collet-Eckmann to have plenty of space in Fatou set?
Yeah, but the measure should be 0. The measure is 0.
Only this porosity.
Yeah, I don't think I need to use that.
Another question. Can you replace weak recurrence condition by something like Tsuji condition, that in average logarithmic scale we are not too close to critical points? So
we are working
not
on
closest approaches, but average.
I see. Yeah. We are working on to improve this to drop the slow recurrence completely, more or less, at least for the quadratic family. We're not quite ready yet, but of course, every rational map has some alpha, right? So this is like
in average, every rational map has some alpha.
Yeah. But I think every rational map actually has some. Every Collet-Eckmann map has some alpha.
Yeah, but that's easy.
Yes, easy. Yeah,
but in average also, which is not so easy.
Okay. Yeah. In general. But yeah. So
Tsuji introduced it in his papers on maps of interval.
Okay.
as additional condition to Collet-Eckmann.
Okay. So the answer is officially I don't know, but we are trying to tweak this. I think so, if possible. Yes.
Thank you.
Any more questions, comments?
Thanks. Thanks, Magnus. So the delta tilde there at the end, that will depend on the size of your starting, the size of the starting square, the parameter neighborhood you can take will depend on delta tilde.
Yeah.
Have you a relation between the two?
I didn't compute the relations. No, I didn't compute any relations. Just that this goes to 0. This tends to 0 as this eta and epsilon tends to 0.
Okay.
Yeah.
Cheers.
Any more questions? If not, then let's thank the speaker again.
Thank you.
The lunch starts in 11 minutes. So, and we reconvene at 3 o'clock.